In this question, you're asked to use your knowledge of the special theory of relativity to determine the length of a moving spaceship as it passes by your stationary space station. The spaceship is moving at 0.8 c, and that is 8/10 the speed of light. Now, once objects start moving at fractions of the speed of light, then we have to use Einstein's special theory of relativity. Einstein was the man who totally redesigned space and time in order to keep the speed of light constant in no matter which reference frame it was being measured. And because of that, these things happened. So what did Albert Einstein actually say about this? Well, he said the following: objects moving past you, fractions of the speed of light, will be observed to be shorter. So what exactly does that mean? Well, we have the situation here. We have a spaceship travelling at 0.8 c past a stationary observer, which is you. And the equation we're going to use is the contraction equation for the length. So let's assume that L dashed is equal to the length that you measure of the spaceship which is moving past you. And that is equal to the actual length of the spaceship when it's not moving, multiplied by the following 1 minus v squared divided by c squared, where v squared is the speed of the moving spaceship. Now, as you can see, the speed of the moving spaceship is written in this form here, 0.8 c, and that makes it easier to do this calculation here, because this particular part of the equation, v squared divided by c squared, ensures that if you put in the fraction of the speed of light in terms of c, the two c squares will cancel. Let's try it out. So the length of the spaceship which you will observe, you'll measure as it moves past you, is equal to its normal length, the length of the spaceship when it's at rest. In that case, it's going to be 500 meters, multiplied by the square root of 1 minus, and the speed is going to be 0.8 squared, c squared, divided by c squared. And you can see the two c squares are going to cancel out, and you're going to be left with the following: 500 times the square root of 1 minus 0.8 squared. Now, if you do that in your calculator, you end up with the actual length of the spacecraft as you measure it is going to be equal to 500 times the square root of 0.36, which gives you an answer equal to 300 meters. So even though you measure the spacecraft as it passes you by, you will see that it's not going to be the same size as its length if you measure it when it was stationary. The stationary length of 500 meters, you will measure as it goes past you a length of only 300 meters. The length of the spaceship has contracted, and this is to keep in with Einstein's theory that the speed of light in any reference frame must be the same. In order to do that, the length of objects in the moving reference frame must reduce, and the time intervals in the two reference frames, the reference frame you're looking at, must increase. Albert Einstein's special theory of relativity, redesigning space and time. In this question, you're told that a spectral line observed on the Earth has a wavelength of 400.0 nanometers. That same spectral line observed in a distant galaxy has a wavelength of 400.4 nanometers. So the wavelength we see has in fact been stretched, it's been made longer, or as we say, it's been red shifted. And that tells us, according to the Doppler effect, that that galaxy is moving away from us. Do you remember the E of the car moving past us? So the fact that the wavelength's got that bit longer means that the galaxy is moving away from us. Now, we can define the Z shift from the following equation. The Z shift is equal to the observed wavelength you see in the distant galaxy take away the wavelength which you observe in the lab, the source wavelength, divided by lambda s. So we can plug the numbers in and we have Z equals the observed wavelength, the one in the galaxy, is 400.4 nanometers. We'll leave the nanometer sign out for the moment. Take away 400 nanometers and we have to divide that by 400 nanometers again. So the Z shift becomes equal to 0.4 over 400. And that works out to be the following: 1 times 10 to the minus 3. Now notice there's no units involved because the Z shift ratio is a ratio, and a ratio has no units. But what can we do with that Z shift ratio? Well, we link it up with the other equation. The Z shift ratio is equal to the speed the galaxy is moving away from us, or the recessional speed, divided by the value of the speed of light. Do a little bit of rearranging and we get the recessional speed v is equal to the Z shift ratio times c. And put the numbers in and we have 1 times 10 to the minus 3 for the Z shift ratio, multiplied by 3 times 10 to the power 8 meters per second. So we have the following recessional speed of the galaxy: 3 times 10 to the power 5 meters per second. So isn't that amazing? Just by looking at the spectral lines on the planet Earth and matching them up with the same element in a distant galaxy, we can work out the Z shift ratio, and ultimately we can work out how fast this galaxy is moving away from us. A little bit of extra revision. If we find out that the Z shift ratio is going to be minus, it must mean that the galaxy is moving towards us. That means it's blue shifted. These are one things you have to sort of remember for your exam.